We can fix it. Just move from this side.
Okay, are we ready? Is this on? Okay, this is for the web. Okay, I have to shout because this is for the web. First of all, thanks to everybody for coming. First of all, we're going to have a short presentation by the IDA student chapter who was not able to be at the convocation, so she's just going to give you a little quick synopsis of what the International Interior Design Association does, and then we will move on. Shout.
Hello, my name is Shelby Patterson, and I am president of IDA, which is the International Interior Design Association. And it is a new student chapter at LTU. And we have many benefits in joining our chapter. And today I'm just going to share a few reasons on why. We do a design competition every year, and it is about social. They're designing a social station, which is a co-working office space, and the design competition ends on February 6th if anyone's interested. We also do a mentor program every year, where they place you with a firm and you do a job shadow for the time being, and the deadline for that to join is February 1st. And then we also do Finish to Fashion every 2 years. And this year we teamed up with Area Studio in Southfield, and we created an outfit made out of finished products from MDC and OFS materials. And the fashion show took place at the Gem Theater in Detroit, and it just brings people together in the industry. And then finally, we do an event. We go to NeoCon, which is a large trade show expo in Chicago, and happens at the Merchant Mart Center. It showcases new products coming out this coming year, and this expo is happening June 12th through the 14th. And last year 9 of us all went. We got on a train and went down to Chicago and spent the time there. And then I look forward to anyone joining our membership, and we have plenty of events happening this semester, and feel free to email me if anyone has any questions.
All right, just before Karen Swanson introduces our speaker for the evening, at this time of year we also acknowledge some of the work of some of our very high-achieving students within the college. Let's see if I can. And this is through the Tau Sigma Delta Honor Society. This is the only accredited honor society in architecture and the allied arts in the United States. And I'm very happy to say that we rechartered last year with our incoming students, and I just have a couple lists here. If any of these students are here, I'd love for them to stand up. We also have our new incoming inductees for this new academic year. So a round of applause for these students, all of whom have... all of whom have achieved not only a very high GPA, but really stellar credentials across their work within the college. So congratulations. And I will turn it to Karen, and she can introduce our speaker.
Thank you. Okay, I'd like to introduce Zhangmei Wu, who is an artist and an assistant professor of design at Indiana University in Bloomington. She works as an artist and designer, and is interested in how folding can be expressed mathematically, physically, and aesthetically. She has an urban design degree from Tongji University in Shanghai, MFA graphic design degree from Indiana, and also her interior design degree from Indiana. So she is multidisciplinary. So we're very happy to have her, and her work is exhibited, both her folded light art in Gallery A210. So I really encourage you, if you haven't seen it yet, to go down. When it's dark, it's beautiful. And then we also have her work exhibited down at the DCDT, a very large installation, also lighted, and then some examples of her study models that are along the wall. So it's definitely very worth your while to go down there to see it. So thank you, and so you don't need this? You got the mic?
Oh. Yeah, thank you. Thank you so much, and thank you for having me here. I want to especially thank you, Karen, for sort of working with me over the weekend, right? It's just weekend, right? And Steve picking me up, and all these great things you guys have going on here. And this is the first time I'm here. I'm very impressed with this many people come to listen to me, and sometimes you go to a conference, right? By the time you get to speak, who knows who's going to show up? So I'm really excited. Very excited to be here. So my talk, I will be talking about folding, paper folding, and rhythm and algorithm. And sort of the subtopic is origami inspired generative form finding. So you guys all know about rhythm, right? So I don't have to talk about it, but algorithm, anybody have ideas what's algorithm? If you're in computer, step-by-step procedures in computer programming to achieve a certain functions. So I do this, I use algorithm not just in a digital sense. I also use it in a sort of analog sense, refer procedures, these step-by-step procedures as you accomplish making your paper models, right? So here I'm trying to link the analog world, which is physical world, to the digital world through algorithm making and through form finding. Okay, so that's my name, John May Wu. Always try to advertise myself everywhere I go. My website, johnmaywu.com, and I also have a brand name. It's called foldedlineart.com. And you can check me out on both websites. And, if you want to follow me, you can like me on Facebook. And okay, so let's get started. First of all, I want to talk about my inspiration, how did I get started, where my inspirations are from. So I'll show you this image. How many of you guys know about this image? Raise your hand. Okay, yeah, all right. Some of you guys, okay. So this is a hanging catenary chain model by Antonio Gaudi. And how many of you guys know Gaudi? Oh, yeah, okay. So if you've been to Barcelona, check this out, right? This is the model for Sagrada Familia. I don't know if I say it right. I'm not a Spanish speaker, but anyway. For each of the building, he will make models, right? And for this very complex structure, he will build these models. And basically, they're just chains. He hangs these sandbags on the chains to create a natural, what we call optimized or, a catenary curve chain. And he will put a mirror underneath the model, and he sees a reflection. And from that reflection, he built his beautiful buildings. And I don't have a picture. I assume that you guys already seen this picture. So, but anyway, so his approach is very interesting for me and for many architects and designers nowadays working because he's sort of not really. Of course, back then there's no computers, and he really prefer models over drawings. So you can see his approach. And then I'm going to show another picture. And I don't know if you guys know where this picture is from. So this is from a book on this architect called Fred Otto. And how many of you guys are in architectural program? Raise your hand. Yeah, Fred Otto. Yeah, Fred Otto is he won the 2015 Pritzker Award, right? So this is Fred Otto's experiment. Again, he's a guy. He was inspired by Antonio Gaudi. And for Fred Otto, he's also back in the 70s. He already started using physical models and also working with physical agents to sort of finding, try to understand structural forms, such as minimal surfaces. So he will experiment with soft films In this example, he was experimenting with wool. He was trying to understand how to create optimized two-dimensional structures for city, so the urban networks. So he will create a model with the wool and tension it up, and then he will release the tension and put this frame with this wool woven on the frame. And he will dip that frame into a tub of soap, like you see on the left side. And naturally, the wool will start to, some of the threads will start to connect together, and you start to see this very interesting voids and bifurcation, sort of this natural process resulting from the natural agent working with the natural material. And then on the right, you see how he used, pretty much, same thing, material wool, but in this time he would dip into glue and as well as the syrup, and create this very interesting sort of forms. And he's using this in order to understand not just two-dimensional forms, but as well as three-dimensional cancerous bone structures. He's trying to do this as a way to understand those structures. So those are very inspiration for me. So I, as an artist, I have been working with paper. This is not a very good picture, I can tell. I just have my camera, iPhone, take some quick snapshot. And this is up in DCDT, right? Nice, I love that name. Such a nice DCDT. And I work with paper. I fold them, and I can manipulate them. I can roll it. I can pinch it together. I can bang it. I can experiment the material in a physical space. And what I'm doing with my hand, I can tell you, is very, very difficult. I mean, actually, it's right now, it's impossible to do it in computer, right? To fold a piece of paper is very easy. And just this afternoon, I was doing some very simple paper folding workshop, right? Just with paper, just hands. You don't even need scissors, nothing else, just hands and paper. And you can make some really easy paper folds. But to model those paper folds in computer and to understand that, what's happening mathematically is actually a very, very complex process. And because of this, because this easy way of allow one to work with this particular material, and because of the complexity that is embedded when one working with this particular material, because of this, I am particularly as a designer and artist, I'm really interested in paper folding, and that's my approach. And you see some more paper, and this is just really random, sort of when I put this together on the wall on the DCTD gallery, I thought that was the most interesting part because I don't even know what I'm doing. I'm just playing with my paper. I bring the paper model just in box, right? Just in 2 boxes, and I just pick one up. Me and my student assistants, we just put them up and just play with it to see what kind of form emerged from playing with the material. And all this process, all the model on the wall only took us about 1 hour to finish. And I thought it's really fun. It's more fun than putting up that large structure. So it was very interesting for me to play with the small model. So I want to talk about paper folding now. I want to tell you a little bit about origami. And what is origami? And you guys are all familiar with origami, right? Yes? All of you guys done origami somewhat? Yeah, play with it. I want to show you this picture here. This is a paper crane, right? Yeah, you guys familiar with this type of origami? It's very interesting, popular. It's like a child's craft, right? Or some sort of craft activity. In this picture, it shows on the right, you see the quiz pattern of that particular crane model. On the left is a digitally modeled crane model, and it's done by computer simulation using Jun Mitini. Jun Mitini can really is a professor in one of the universities in Japan. I think it is in Kyoto, but I might be wrong. So he had created these computer algorithms so that if one inputs the quiz pattern, and then you can get a result, you can get this, you know, and this paper crane as a three-dimensional model. Very interesting. So this type of paper folding is what we call a human activity, right? So we human, when we invented the paper was invented in China about 2,000 years ago. When we invented the paper, we started to play with paper, create an object like that, right? So this is a human activity. And I want to show you another type of folding, right? Which is not done by human, and sort of you can find this type of paper folding or this type of folding pattern in the nature. And this is one of them. Again, this is a computer simulation of a Miura pattern. And this simulation is created using Tamahiro Tachi's free-form origami software. You can download it from his website. And you input a two-dimensional structure, and you know, the program will allow you to simulate the folding, and you can see the folding of, you know, and the deployment of the folding of in different stages. Very interesting, but the software, I want to warn you, if you're trying it right now, is very, very limited. Like I say, it is still a topic that attracts many researchers in mathematics, in computer science, in engineering. And they're all working this together, try to understand what happens to paper when it's folded. You know, in mathematics, paper folding can be understood as a problem, what we call isometric embedding. You guys probably heard of the word isometric, right? Isometric drawing in architecture, isometric embedding, that's a mathematical term to describe the, you know, the transformation that happens when paper is folded. But anyway, this pattern is called Miura pattern. You know, it's discovered by Japanese. He is an aerospace scientist. Let's just put it simply that way, Miura. And he discovered this pattern around 70s. Okay, so we as human beings, pretty amazing, you know. We did not understand how to fold this pattern until 1970s. And well, he was actually, the way he discovered the pattern is he looked at tons of pictures. You know, he was studying this formation, this geological formation. As you can you see some similarities between this type of fold? You can start to kind of take that sort of this zigzag, this form, and the natural form, this mountain form. So he was taking tons of pictures, you know, of this geological formation, especially mountain formations. And he was also, they say, you know, that was said. They said that he was looking at the wrinkles of old man's brow. And he discovered this pattern, so pretty amazing. And nowadays, the scientists are very interested at, you know, how mountain folds. And in fact, this is a special study called orogeny. If I didn't pronounce it, you know, if I'm saying it right, called orogeny. And they study how, you know, these different protonic, you know, plateaus and clyde, and what caused them to create these different type of formations. Very interesting. So taking that, you can see that, you know, this type of folding is quite different than this type of folding, right? So in origami crane, you when you fold a piece of paper, you fold one crease, and then you make another crease, and then you make another crease. So crease by crease by crease, and one has to follow another. And in this type of folding, all the creases sort of simultaneously come together. So in a what we call, or especially scientists call, a self-organized way, right? So this is the type of folding that I personally am very interested in as an artist and as an origami artist. So I'm giving you some examples of this type of folding, and those are all just sort of discovered. Earliest ones, like I said, this is an alternation of the Miura pattern. The one in the middle, I guess you guys can see. Can you guys see my mouse? No. Okay, so the Miura pattern here, that's the one I showed earlier. That was discovered somewhere around 70s. And this one, water bomb pattern, was also discovered around the same time. Yoshimura pattern was discovered by, again, a scientist named Yoshimura when he was studying the buckling of thin wall structures, the natural. So he was in engineering. So when he discovered this one. And then there's also more. This is another pattern, again, by an Japanese scientist engineer. This is called helical triangle patterns, or you can call it Nojima pattern. So all these different type of patterns. This is the most interesting pattern, and those patterns are discovered as scientists, not by artists, right? They're by scientists who study what happens in nature, natural phenomena, and when they arrive at this. And this is a very interesting thing for me. All these patterns on the left, you see how the pattern is folded, and then on the left and on the right, you see, on my right, is you see how this pattern is folded in flat shape. So the pattern is what we call rigid foldable and flat foldable patterns. And this pattern have many applications in engineering, in architecture as well. And before I go, I want to describe a little bit about, the kind of mathematical principles that people found in making those flat foldable, rigid foldable pattern. So this is one of the example here. This is a pattern that I sort of just create myself using simple geometry. And this pattern is flat foldable. That means that I can collect this structure and then twist it and then flatten it into a two-dimensional shape, right? So for flat foldable origami design is a key to understand something what we call Kawasaki theorem. So I have a wrong spelling here, I'm sorry. So Kawasaki theorem is states that for an origami pattern to be flat foldable, the number of lines connecting to a single inner vertex, that means the point where the crease lines meet, must be even. So I have some wrongs, so I'm sorry about that. Must be. So here is the example here. So what you're looking at here is a vertex, right? So each of this pattern, if you unfold, you can see them in two-dimensional, but right now it's a three-dimensional structure. So taking this vertex, for example, if you count the crease lines that connected to the vertex, you will find that right now they are 6, right? So this number must be even. So you can have 4, you can have 6 or 8, right? It cannot be 3 or 4. So that's the first condition of Kawasaki theorem, right? For a pattern to be flat foldable. And the second condition is the sums of alternating angles are 180 degrees. So what that means is taking that vertex point and you flatten out all the angles, and you add the alternate angles. So this is a drawing of that, right? So I have 1, 2, 3, 6 Chris-Knight connect to that vortex points, and I'm taking the alternate angles, which is, for example, theta 1, 2, 3, 4, 5, right? So when you add them together, you need to add theta 1, alternate 1 is theta 3, and then theta 5. And if you add them together, it equals to 180 degrees. That's pi, right? So, so this condition need to be met for a pattern to be flat foldable. And you can imagine sometimes can be very challenging. And actually, till these days, nobody can come up with a design. You know, if you say, okay, I want this particular shape here, can you create a quiz pattern that is flat foldable based on this particular shape? So far, there's no answer yet. But we know that if you give any, if any shape, any arbitrary shape, it can be, organic, whatever, a face or whatever, any shape can be folded. And that has been proved. Any shape can be folded from one single piece of paper. So this can be very complex, because what happened here, what you want to pay attention in this type of constraint is all the vertex, not just this particular one, all of them need to satisfy this Kawasaki theorem, right? Because you cannot just say, oh, this point satisfy, and these two, the other point don't satisfy, do not matter. It doesn't work that way. All the vertex points need to work together globally in order for a quiz pattern to be flat foldable. So that make some really interesting, challenging issues for designers and for mathematicians and artists who are trying to work with paper folding. Right? We are still, people are still working on solving that problem. So here give you some sort of simple examples of what I mean by that, flat foldable. So if you look at this on the left here is origami pinwheel design, origami pinwheel, and it's a flat foldable design. Because why we know it's a flat foldable? Because we notice that we have a right triangle here, and we have another right angle here. So we know that if we add those together, it must be 180 degrees. And because we only have, because all the angles the sum of all the angles is 360 degrees. So we know this point is flat foldable. And you end up with something really simple like that. That's an origami pinwheel. But then if you change your quiz pattern, you change your angle, and you can tell immediately that is not a flat foldable angle, because the alternate angle, when you add the alternate angles together, they will not equal to 180 degrees. So it's just a very simple explanation, simple way to understand how to create a flat foldable design. And you guys know the advantage of flat foldable design, right? So you make something, it come in compact, two-dimensional shape, and then when you need it, hopefully you can just push a button and you become three-dimensional shape. And it has to be done in space structures. So architectural space structures, they all link, right? People are doing in space, it connects to us. What we're doing here on Earth, I think it's all connected. And today I want to focus on two, particularly two patterns that I discussed earlier. One of them is what I call water bump corrugation tessellation. And this tessellation was discovered by Fujimoto, again a Japanese origami artist in the 70s. It's pretty amazing. It was when it was first published. And I can see, what I do as an artist, as designers. I was just playing with with the students this afternoon. We folded this pattern from very simple diagrams, right? We go through just simple pieces of square, and then we fold it, and then we try to connect it together. It's really amazing to me, like why it's so late, like almost in the 70s, and then we found this pattern. It's pretty amazing. So as an artist, I play with this pattern pretty much. I fold it, and I try to see what I can get out of it. Like I said, analogically, pretty much. So I take the pattern, I fold, and as I fold it, I discover something really interesting, and I alter the pattern a little bit. I change the proportion, and immediately I discovered that from a flat piece of paper, and on the diagram A is the pattern in a flat piece of paper, as you can see, and those examples are the examples that when I folded them, and you can see that it creates very interesting surfaces. Is what we call double curvature surfaces, right? What I'm changing is I'm changing the Gaussian curvature of that flat piece of paper into something that is a torus that has double curvatures, right? And this is a piece I did earlier in 2014, and this piece just won the award by the American Society of Mathematics for best sculpture in mathematical art. And I was actually pretty happy about it because I'm the first person, discovered that I can use that pattern to create the torus. In math is a very interesting thing in math, because what I'm doing here is pretty much try to solve a big problem here, or try to demonstrate, or try to understand how to visualize Nash problem. And that John Nash is a famous mathematician, right? I don't want to get into it. Lots of mathematical sort of argument in this. But what John Nash is saying that, okay, yes, the Gaussian curvature, when we change, we can embed a piece of square into torus, right? Do this. I metrically embed a piece of square into torus, and don't ask me what that means mathematically. But he proved it mathematically, but he never visualized it. He couldn't. And now until recently, in just last year, 5 mathematicians working together finally come up with some sort of visualization of John Nash's problem. And this is my version of visualization of John Nash's problem. Therefore, I think that's why I won the award for that. So very interesting, but here I'm not using any high-end computer models, right? I just play. And you see how sort of this very interesting material property sort of emerge as I play with the patterns, right? And taking that further, that's how I work, right? As an artist, I break apart. I wonder, how do they discover this? Do they discover it by, sort of making the complex two-dimensional pattern and then draw it and then fold? No, I think people discover the pattern, they work that way. They actually work in a way that is reversed. They start with small seeds like this, right? Small seeds, like what I'm doing here. I'm taking this pattern, I alter it, I add another pattern. This is a small seed, and I can tell this is my own design now, my own quiz pattern design. It's my own inspiration of create what we call flat foldable a design from one single piece of paper, from just one single piece, and that paper, sort of tessellates in plane as well in three-dimensional space. And you started with single seed, and then you figure out ways to connect the single pieces of paper together to create a system. And once you have a system, you find, oh my gosh, the system is a lot more amazing than the individual seed that you start out with. And this is a principle that we know in nature, you know. Everything starts with something very small, very simple, right? So now I move to this. This is, you know, what it shows is the folding pattern of the previous pattern I did that is folded into one large continuous sheet of paper, one single sheet, no cut, right? No cut. And this shows some sort of artistic inspirations of working with that pattern. So I sort of, you know, again play with it and sort of, you know, taking it and gather some edges together, perhaps pinch something together to see what kind of forms I can get, you know, from these inspirations. And you can see that the pattern is completely flat foldable, you know, in the diagram on the left here. And then, you know, more sort of inspiration. Huh? Okay. Yeah. Well, you guys have a great computer monitor projection. Things I don't see on my screen, I can see it on the monitor. I'm really impressed with what you have. Really. Have you guys been to Indiana University? Anybody? No? Do you guys know? Yeah. Bloomington? Yeah. My friend, my friends from Indiana, yeah. But actually, we don't have such a nice facility. I'm very, very impressed with you guys. But anyway, so inspiration, you know. So some details. So the next thing is, okay, I know I can fold, I can do things, but can I understand it more rigorously? You know, can I understand the mathematics behind it? Right? So I'm interested in that as well. But you see, I'm not trained as a mathematician, right? And you know, I talk a lot about mathematics a lot. I use many terms or whatever. I'm not trained. I'm not. And really, I'm not. I don't think I can get through linear algebra, you know, myself. I can, you know, calculus is way beyond me. I can understand the concept, but to really use it as a mathematician, I don't know. So I work with mathematicians. I ask them. I say, "Are you interested in this? Can you help me?" You know, that kind of stuff. So I work with a couple mathematicians at my university, Indiana University, and here it's just a very simple task, right? And you guys notice this is the same word-bound base pattern that I used earlier. Right? And here we are in the digital environment right now, and we try to model it. And I just have one unit, right? I just have one unit. And I'm using these parameters to control this unit. For example, I can change the folding angle, you know, try to make it fold, and I can also change the ratio of this length and this length. So it gives me different type of modulus. So use this to control. So here's what you can see. Oh my God, it's already so complicated, right? Those are the algorithm that I use in order to just, you know, model one single unit, right? It's kind of, well, gosh, too much. And you know, and just one single unit is supposed to be very simple, right, to understand that. And I need some linear algebra. And luckily, you have the, you know, mathematical solution for this particular, to understand the x, y, z movement of these points in space. It's not too complex right now. You know, I can enter it I'm in Rhino and Grasshopper right now. And I can enter the formula in there and can model it in Rhino. But if I want to connect two modules together, and I want to understand when two modules are connected together, and I want to model that, whoa, the task becomes very complex. And if I want to model three of them together, because you have to remember, if I model this type of simple geometry in computer, you have to remember, right? It's an isometric embedding problem. That means that all the length geometries in my two-dimensional design remained consistent in three-dimensional design, right? In 3D structure. So that is sort of the key aspect. And you have to use some high-end geometry, linear algebra. So this is the formula I'm getting now. Just 2 modules, okay? By the time we get to 3 modules, I can't do it in Grasshopper. So my partner in mathematics, he can only do it in Mathematica. This is the mathematician's program to visualize geometry. Very interesting. And he told me that, you know what, I can't even print out the formula to you because Mathematica will not even output the formula for me because it's so complex, just 3 modules. So you know why we are interested in this problem? Because we want to understand it. How can we do it, right? So this is, I'm trying to input this in Grasshopper. It was a mess, but it's an ongoing project. I can tell you I don't have an answer, but you know, since I'm not a mathematician, you know, I'm interested. I wonder about it, but I move on to other things, right? As artists, so I move on to something else. So that's why I move on. I'm taking that module, like what you see earlier, the water-bound bath, you know, the same thing. And I manipulate that module in 3-dimensional environment, in computer, digitally, through algorithm program. And this, you see a series of different type of design, parametric design that based on coming from these small seeds, small water-bound bath seeds. So I can continue more. So this is what I show you, you know, in how in the algorithm environment, this is one of the seeds I start with, right? And please remember, I messed up this module because this module now cannot be flattened anymore because I'm in a digital environment. I distort, it still remains the visual characteristic of that module, but it cannot be flattened anymore. It's not the flat foldable shape. So this is what it shows. And here, you know, I try to make into some sort of product design. And in this particular example, it made up of 128 modules. And it's a symmetrical design, so I have 8 unique modules. And you can see this design in your gallery. I don't have to. And these are the patterns of unrolled patterns that were sent to a laser cutter to cut. And then from there, I fold and to connect, create the visual of that. It's an exhibition in Tokyo, no, actually Toyota City in Aichi Prefecture in Japan. You know why I sort of love to work with Japanese artists as well as scientists. I've visited there twice now, and to study paper folding as well as paper making. I'm interested in how to actually start at the material level and start to create a material for my paper folding design. So this is some of the pictures. I'm going to run through this pretty quickly. Some of the details, I'm using a type of paper that is actually made in Japan. It's called kozo paper. It's very beautiful paper. It's made from a natural fiber, inner bark of a type of mulberry tree. And they have these beautiful traditions of making paper, handmade paper. It was beautiful, and I actually learned about the process of making the paper. And this one particularly is a type of paper that Japanese were used as soji screens. So it's soji paper, actually, and I repurpose it for my own design. It has a nice polymer in the middle. But anyway, oh my God, am I running out of time? Okay. Wow, 15 minutes left. I have to go very fast now. Okay, okay, some designs. But you see, what happened is because I'm coming from the origami idea, and the whole entire structure can be flattened into a shape like this. This shows that what you see earlier now is flattened into a 2-dimensional package, and that's the material. Okay, so the next thing I want to talk about quickly, now I don't have a lot of time left, is this pattern. Nojima pattern, or you call helical triangle pattern, and how I work with that pattern. So here is a picture, sort of showing you the possibility of the pattern, showing you the pattern in 2D, and showing you the pattern, fold it as well as flatten it. So what can you do as a designer? This is already a long pattern, sort of pattern, right? What can you do? So as designer, you can change the pattern. You can create designs like this, like what I do here. I just take the pattern, I manipulate it, I distort it, and all these are done analogically, right? Analogically. And I play with it, I shape it, and just to see what kind of potential it creates. I'm working towards a project I call Ruga interior skin. And Ruga is a Latin word for making wrinkles. So it's a word that used by material scientists, and I found it's a beautiful word. So I use it. And if you want to know about this project, you should go to DCTC. I have a huge installation of Ruga skin, the latest iteration in display, and I also have a description about my project in much greater detail. And I don't want to go through it. All this again by showing you this. So I experiment it also digitally and try to simulate that folding. My idea is to create something that is very flexible, can be used in different scales, try to connect the body to the space. So this is the whole concept of how do we make material that is flexible, that is more, sort of akin to our own skin, right? Our skin wrinkles, right? So can I make something that is also based on wrinkling and folding ideas and for fashion as well as for interior design? And then you see that once I fold, I can manipulate, I can roll the paper, I can see what kind of forms I can generate from that 3D shape, and you see the models there. And then I take that and start to think about, can I do this larger? Can I make it into an interior skin? And the whole idea of the interior skin, I'm teaching in an interior design, interior architecture program. I'm going to take that concept, talk about interior skin, how it's different than architecture skin. All right? Architecture skin, you have to negotiate inside and outside, but interior skin doesn't have to. It's an inside structure, it's flexible, it's closer to the body, it's for people to touch, to feel, and to enclose the body, to protect the body in a way that is a lot more intimate than architectural skin. So I see, different type of thing. So here's what I started out making it. Making in different scales, quarter-inch scales. As I start to fold them, this is my first try. This is in 2014 or 15. After you can see I was trying to fold and try to move the structure, but it's so big. And I realized, oh my gosh, at that scale, we cannot fold the structure anymore. Fold any at all at that scale. And so we make a monster, and then we just toss it out to the trash can, pretty much to the recycle bin after we make it, because it didn't quite work. But it's a good way, because I experimented by hand, and I discovered, there is limitation, right? And this type of stuff, you can only do it by hand. And you can see some of the detail. And I started making more details, and I started experimenting in different ways to creating them. And, I involved a lot of times, I through my research found I will hire my students, or I involve my son. Here's my son, 13 years old. Now he's 15 right now. He's helping me try to fold it together. And you can see how, the patterns when it's flat, it's fairly large, 20 feet long, and how it's spread out in the studio. And here we're trying to making it to, fold it, and we try to use whatever we can, like the trash bag, to hold this up and to manipulate the folding foam in space to see what kind of spatial configuration we can generate for this folding foam. And here we are, doing more experiment. And this is sort of the final sort of configuration that I wrap. And of course, I started with small-scale models, right? I didn't show. I will show you a small-scale model earlier. And that's me here. I'm trying to mark the, the movement of the structure, because it's like a wing, right? Opens like and this piece I call Ruga's one. So I'm marking it with my body. some details. And then I'm going on to make another iteration of this, and this is now in a big touring exhibit. It's called Above the Fold, a New Expression in Origami, and I'm touring with 8 other best lamps in origami, pretty much. If you guys know about them, Paul Jackson, and Robert Land, Eric Deman from MIT. I don't know if you heard of their name. Eric and Martin Deman, they are also in the show. And some other very great. And I'm really fortunate to be involved in a project like that. It has been traveling in the United States in many different places now. Next thing, I'm going to go to Allentown in Pennsylvania to install this piece. So here comes, the museum. They have created this large crate, 20 feet long, and inside the crates, this is what you see, the panels are flat foldable, sitting inside the crate, and that's how you move the structure. It's flat foldable design, and it travels. And this is the first installation in a Springfield Museum in Massachusetts. If you pay a little attention, there's a little model here, the paper model that I started out with. That I actually take with me to all the installations, because that's the easiest way for me to visualize how the piece is going to become. Each installation will be a little different. So this is sort of this analog, artistic type of experiment with paper folding, and you can see some of the installations in different museums. This is again in Springfield Museum in Massachusetts. And this is in sort of a close-up shot in a historic museum in Norfolk called Hamilton Museum, Museums and Garden. Very interesting, beautiful place if you haven't been. And this is in another museum, a bigger museum. So after I experiment with that, I start to think about, okay, what can I do? Can I do, again, rigorously? Can I understand this folding? Can I understand this pattern from a different angle, from computational design angle? So, and then I start to explore with that, in parametric environment. And here is sort of my sort of way to think through the process. What can I do? What kind of forms I can generate? Like I can generate parametric surface using mathematical curves, that can work with the human body. And I can parallelize those parametric surface using the folding pattern. And then, of course, with paper folding, I have to think about structural problems, because a paper folded structure is pretty much a folded plate structure. The folding angle actually is very important for the in terms of making a structural sound object, a piece. So I have validated those angles, and all this can be done parametrically. And I also need to unroll the panels for fabrication digitally. And you can see how, can I use curves? And those are some simple curves. I can just use Grasshopper's simple mathematical curves to help me model. And this is sort of a view of the model. And this is the piece that is currently in display in DCTC right now. In the parametric environment, and it shows how the panels are connected, unroll it, and I of course go about how to make them. And this is a workshop I conducted at Indiana University. I asked my students to put it together, basically for the first try. And of course, I was the commander in charge, told them what to do, and nobody knows what to do, and you can see it. People are using their bodies, holding up the structures, all kinds of crazy stuff. But it's all learning process, right? Try to figure out how can we fold at the large scale. And then sort of first iteration, you can see that, we see some structural problems we need to fix. And all these are done through this process. You can say it's not as rigorous, but as an artist, this is the kind of tools I use, this kind of work sort of process I work through. Next thing I will do is I have to work with engineers. I will probably send my structure, send my design to get a finite element analysis done for my structure and then understand the structural potential. But right now I'm just complex, and this is what is done with a smaller model that is in a museum in Midland, Museum of Science and Art, and I took that one down and. On the panels right now. Karen, you have the panels. So if you guys are challenged enough, you can try to put that together. So that's what it looks like when you put together. So now we move on to the exhibit in DCTC. And in this example, I added interactive color work because I am pushing that metaphor of skin a little farther. I want my skin to be responsive, to be able to gather information of the environment and then display the information somewhat. But artistically, I'm just doing it with colors, right? So there are sensors installed, Kinect sensors, and you will sort of understand people's movement in space. And that depth data, that information is input in processing environment, and the processing will produce, different type of colors. So if people pass through this, into different zones, we actually zone this into different things. If you pass through this, and I haven't really tried myself, but you pass through different zones, and it's supposed different parts of the piece will animate. Depends where people are. So that's what we are doing right now. I heard lately that the computer crashed. Somebody need to restart it, and I don't know what's going on right now with this piece. But we have tested before. We know it's working. And I'm working with a PhD student in HCID, Human-Computer Interaction Design. He actually did lots of the programming and processing with this piece. But we work together, in some ways as a design team. And you are wondering how I put that piece together, so I can show you some secret. We actually, to put that piece together, we are not just holding up with our human body anymore because there's no precision in that. It's just sort of ad hoc process. So right now we're building a frame, but then we build a frame, we use very cheap material. It really doesn't cost much money, just plywood and dowel rods and cardboard papers. And we find the points and we make these frames. The night we got here in Detroit, we put it together, and you can see how it looks like, the structure. The panels are all there on the floor, and that is the frame, the inside frame. It helps us, guide us as we connect our panels together into large structures. So this is what you see, the end, put it up, and I just take some quick snapshot. I'm hoping, there's some professional pictures taken for me. So there's some views of this piece. It's constantly changing, it's moving, twisting, because intention twist the folding pattern and to create this movement. And some of the night view again in that space. Thank you so much for giving me such a beautiful space to display my work. And thank you for being here and for my lecture. And if you have any questions, feel free to talk to me, email me, whatever you like. I would love to hear from you. So more pictures from that show. Thank you. Questions?
Do you have any questions? I know in the beginning you showed how you... Excuse me. In the beginning you showed how you use only your hands and paper to make a paper model, and then you showed how you put it into Grasshopper and Rhino. But what process do you use to get that 3D model in the computer into an actual model? Like what machines, I guess,
are being used to wrinkle the paper into the physical model from the computer model?
Oh, good question. Yes, what machines? Yes, I do use machines. The machines I get is after I talk to some people in origami. I actually talked to Martin Demand, right? Martin Demand, and he referred me to this beautiful, wonderful digital cutter. It costs about $1,000. It's like a hobby type of cutter. It's a small format, 15-inch. And you design your pattern. You send your pattern through the cutter, and it will perforate the patterns for you. And then from that, you can fold easily. Is that what your question? Yeah. So it's a digital. The brand name is called Craft Tech. Yeah. So there are other tools you can use. Right now, for project that big, I use industrial size laser cutter. I send it out to laser cutting to get it done. And this is actually done with both CNC, a drag knife, as well as a laser cutter. Mm-hmm. Yeah.
Thank you.
So. All right.
I don't know if you consider this, but have you used any other materials? It looks like you're mainly using paper, and it looked like maybe that was corrugated on some of the larger structures.
Right. Very good questions. Have I used, as an artist, media is very important for me. A lot of people say, why are you working with paper? Why don't you move to something else? I stay with paper. There are multiple reasons, artistic reasons, and also I think paper is a material that we are so familiar with, and we kind of take granted for this material. We kind of just don't think paper is a good material for design. It's just sort of not durable, can be thrown away. But the thing is, there are so many type of researches are done right now in material science. They are creating amazing paper, technical papers, that you can put all kinds of new type of material with paper, and you're using a process that is really similar to paper making, which is, I don't know. I didn't show any pictures of those. That's what another research interest I'm having right now. I'm working on right now, and experiment with making the material, and through that, sheet material, and what kind of things what kind of new design ideas you can work with by working at the material level. But yes, you can fold using many different material. You can, of course, fold using sheet metals, right? People are doing that. I mean, there are many people doing that kind of stuff. And here I'm already changing. I'm moving from cardboard to plastic corrugation board. This is Coroplast. Coroplast is a brand name. Is a plastic corrugation. And to work with the material, as an artist designer, you have to, one has to figure out the way to work with the material. Because nobody's going to show you how. And nobody showed me how I can work with that and how I can fold with that. So I experiment with that. And actually, my method is so simple, so easy, but yet it works for me. Yeah. So every time you can try, I think there are unlimited possibilities out there. There are many new materials out all the time, and it's just up to you, for you to try it out, to create the kind of result you look for. Yeah. Yeah. Does that help you?
Oh, yeah.
Oh, okay. Yeah. Oops. Yeah.
I have a question. So you talked a little bit about this being a skin for the human body.
Yes.
Have you actually tested it, or looking further into becoming an actual skin?
Oh, wow. Good question. Yeah, I would love to, because, after this one is done, actually my next project is making a piece of fashion, and I have, again, to do that kind of work. I'm working with engineers and as well as computer scientists in my university, and that's kind of work I'm working on next. But to make it into actually try to think about how to design a real, sort of a skin, perhaps use a medical device is something that I am very, 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 very interested in. But I'm not there yet. Yes, good question, yes. Yeah.
So I wanted to, thank you. I really enjoyed the lecture. And
Okay.
You gave us 2 exhibitions and a workshop on top of it.
Yes.
I think I started to get worried at one point in the beginning where you said, well, I can only do these by hand. This is the only way that I can study it. And then at a certain moment, Grasshopper pops up and Rhino pops up into the work. And how, I think what's really interesting about what you show is the kind of investigation, right? There's something, your curiosity is driving what you're doing.
Right.
You never started out with an idea that you would have to learn Rhino or Grasshopper. Right?
No.
So how do you for students who have a project and might be thinking about something, they're really curious, how do you continue to learn new tools and follow, it seems like you're following the path of the project as opposed to imposing something within it. How do you
outside, yes. I describe this as sort of intellectual curiosity, Sort of, how do I do that? So, in fact, right now, if I have time, I will go back to learn calculus. This is something, I actually go through a lot of tutorials myself already. It's just continuous learning because you've done something and then you figure out what to do next. What is next? What can I do? What do I need to learn? And learning is just part of it. And, I do not learn. Nobody taught me about Rhino. Nobody taught me Grasshopper. I pick it up because why? We are in this, what we call machine learning ages. I don't know everything myself. I type in, I ask, I search for it, and this is why I tell my students, they come to class, they are frustrated. Oh, my professors, they don't tell me anything. I have to search up myself. I say, that is exactly what you need to learn, right? Search it up. There are so many answers out there on the web for you. And I go into Grasshopper support group, and I talk to some of the developers, like Daniel Piker, this amazing guy, You email him, and he responds to your email. You feel like you are nobody in that, group, but you email, he responded. It's like, oh, you are working on something really interesting. Let me answer it for you, So almost as I work through this problem, almost everything I need to know about Grasshopper, how to work with data structure, how to work with the data trees, how do I, move my data trees around, how do I, all this, every time I have a question, I type in Google, I Google it, and I find it. That's how I learn. It's really amazing, yeah. And, it's like a machine learning edge, because, other people are giving me information, intelligence. I don't have to find all the answers myself, right? Answers are out there, and there's a huge group out there. So, yeah, yes.
So to make us a look at some fashion of the ground person, would that be almost a completely opposite process from what you've been doing?
Very, very interesting.
The space that
yes.
Thing.
Yes. So first thing I do is I get a dress form, right? I want physical model, and I don't know how it's going to fit yet. So I bought the dress form already. You know what is dress? Are you in fashion? No, okay. Dress form, I just learned that because I'm not in fashion. I know the difference between the dress form and the mannequin. Mannequin is just, posting. A dress form, you can actually pin it. You can manipulate the material through the body structure. And that's the first thing I do. When I know I have to work with the real material, I have to work analogically. But at the same time, I'm proposing my models to get a 3D scan. So actually coming up, we're going to do a 3D scan of the whole body, right? So I am proposing sort of a backwards sort of approach. Getting the body in the digital model first and see what I can do with that, what I can produce. And then after we've done that, I'm thinking about I can, of course, build my material, and then in real material and perhaps paper again. Sorry, paper model. And once I have that, I'm going to fit on the dress form. I'm going to see what other potentials I can create. So this back forth. So there's not a complete disconnect between the analog space and the digital space. You know, the same thing as you see how I work, right? I work digitally, but then I go back to the analog space and I try to figure out how I can pull it up, how I can, you know, make it work, make it stand up. And those are just, you know. And then if it doesn't work, I go back to my digital space and create more forms. Yeah, but very interesting question. So it's sort of different than the traditional sort of cutting the patterns, the dress. I think there's so much sort of improvement and progresses right now in fashion design. It's just amazing. You guys in Michigan, right? Don't miss that great show, Iris Herpen. Have you guys heard about her? Iris Herpen. She is in Grand Rapids right now. Amazing, amazing person. I know about her through another guy that she worked with. She worked with an architect, Philip Beasley. Philip Beasley was just at Indiana University doing a lecture before, and I knew about his work, you know, and then knew about Iris Herpen. And if you look up Iris Herpen, IRIS, Herpen is a Dutch designer. If you look her up online, you will be just amazed. You know, she just used analog approach, mostly analog. She take a piece of material like this, right? And then she gather it, like making wrinkles. And then she fit on the model and manipulate, and then she start to cut the patterns and create her stuff. And it was just, I'm looking at it, like, oh my gosh, that is exactly how I like to work too. Because there's just so many more possibilities than, you know, just working digitally, you know. And yeah, amazing work, amazing work. She's really big. She's an internationally known Grand Rapids. I couldn't make it. I wanted to go, but I'm just so busy, couldn't make it. Any more questions? Thank you so much for your questions. Yeah.
I just want to make one more quick announcement. We were not able to have an opening for the exhibition down at the DCDT because of all this going on. But Zhang Mei has agreed to come back the night before she has to take the exhibition down, which will be February 10th, Friday at 5:30. We're going to have a closing rather than an opening. And this is the first time I've seen these pictures because I left before it was lit, and it's just phenomenal. It's really great. So thank you so much. Thanks, everybody.
Thank you. Thank you so much. Thank you. Thank you so much, Karen.